Okay, so this is one of these caveats where when I'm looking for inspirational ways of demonstrating or ideas of problem solving, I really like this guy, Professor Matt Anderson. There's loads of stuff on YouTube that he puts out. He's also started a paid-for channel. I've got a 90% off voucher being sent to me because I subscribed to his YouTube channel. If you wanted to subscribe and get that, or if you haven't been offered it, email me and I can send you the link for the, if it's something you want to spend a bit of money on. I don't get the impression it's particularly expensive. I think he's just obviously annoyed that he's not getting much money from YouTube. But I would definitely I definitely suggest you get into the habit of looking through his videos. He does have a brilliant way of demonstrating things. He writes on a glass wall in front of him. It's a bit of camera trickery, but it's a great way of being taken through these problems. Okay, so this one here again, this is a good one in terms of intensely looking at the surface area of a sphere. So the recognized value for, let me switch back colors. The recognized value on Earth is 1,390 watts per square meter, which is a considerable amount of power. If you take into consideration that we are 150 million kilometers from the sun, that's an awfully big sphere that 1 square meter sits on. So if you can work your way backwards, you could actually find out how much power the sun outputs. But in this case, so if intensity equals power of area, what would the intensity be on the surface of the sun? Now, obviously, the sun is its own sphere in its own right, and the distance out to the square meter that we're talking about on Earth is on its own sphere. So there's a bit of calculations to do. I will leave you with this problem. So pause. It's on the next slide, the working out. So when you're ready, move on. Okay, so hopefully you were looking at this in terms of working out what the total power of the sun was. I probably gave you a sneaky hint at the start, because if you know what the total output power of the sun is, then you can work your way forwards back to the surface area of, the surface of the sun. So the first thing obviously I've done is I've worked out the area times the intensity on Earth, the surface area of a sphere is 4 pi r squared times intensity. So following that through, we get this value of 3.93 times 10 to the power of 26 watts, which is a fairly large amount of power. And if you want to work out what the prefix is for that, go for it. But then working our way back forward, so we've now got an intensity for the sun and power area. Well, we just need to work out where we are in terms of the sun's surface. So the sun's surface, we were given this figure originally in the question, 6.96 times 10 to the power of 8, which is the size of the sun. So the radius of the sun even. So 4 pi times r squared. We know what this power is because we've just worked it out above. And that gives us the power on the surface of the sun. So 6.46 times 10 to the power of 7 watts per square meter, which is probably why it's quite hot. Okay, so before we run on too much, just a quick reminder. I keep finding people at GCSE who amplitude is from the 0 point, so 0, up to the max. Common misconception, people do this. This is incorrect. Okay, wavelength can be anywhere from here to there. It could be from that point there to that point there. As long as it's a similar point in the same wave at the same phase, that is a recognized wavelength. Obviously, the convention is to use either 0 to 0 or peak to peak or trough to trough. They're just conventions. Okay, both of these have the same amplitude, but which one has more energy? Well, if we look at in terms of the fact that they do have the same amount of amplitude, which we're told they do, okay, we can see at this point here it's imparting energy, imparting energy, imparting energy, imparting energy. In fact, it's imparted pos 4 times, okay, and negatively 1, 2, 3. Let's keep it nice and simple. Negative 4 times as well. So it's imparting energy on whatever it's traveling through, if there's a medium, that is, for the same amplitude but a higher frequency. We've got 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12. So we've got plus 12 times, and I'm just going to make a guess that that's also minus 12 times. So you would straight away see that the two ways, even though they start with the same amplitude, this one here is in fact has 3 times the amount of energy. And if we go back to where we taught you to draw the electromagnetic spectrum, okay, so if we had our radio waves, microwaves, infrared rays, visible, UV, X-rays, and gamma rays. Clearly I'm pro at drawing this to scale. We'd also add in this little arrow underneath. And a lot of people forget about this arrow. And it's the energy arrow. So as we increase the frequency, we increase the amount of energy. It is to do with frequency and not amplitude when we're doing straight comparisons. Okay, so in this slide, we're just going to take an electric charge and we're going to move them. Okay, so I've got a positive charge and a negative charge, and I'm going to flip-flop them. So I'm just going to force the positive charge to go down here and the negative charge to go up there. And at the moment I would have, now I'm probably going to end up drawing over this later, an electric field that looks like this. So this is just a symbol for field, okay, just in case I haven't explained that enough times. So the electric field would be from the positive charge to the negative field. Now we'd obviously have lots of other arrows in, but for simplicity's sake, just keep it a single one. Oh, there we go. I knew I'd draw it in for fun. Okay. Now, as they come together, because I said we're going to move them backwards and forward, that electric field is actually going to get smaller. Not the strength of it, just the size of it. Until eventually, it would get to zero. If they're touching, there'd be effectively no space for electric field, because the charges would be attracted to each other to the point where this would become zero. And then they would swap places, so our negative's gone past and our positive's now gone to bottom, and now our charge is going the other way, etc, etc. And I'll keep following this through. Now, before it swaps screens, so you'll see there's a bit of a pattern starting to occur. Okay, so in this slide, followed on from the last one, I've just taken away the charges and left the arrows there. And you can start to see there's a bit of a pattern occurring. Maybe it wasn't obvious before. There is a 0 point missing here, and there'll be a 0 point missing here. And if I can pull this off, we'd have a lovely, there we go. Oh, it's terrible drawing, but you get the idea. A familiar looking sine wave. Terribly drawn, but you get the idea. So an oscillating charge produces an electric field which is oscillating. It's a sine wave. Okay. So this is how we would do it in relation to time or direction in propagation. So for a given period of time, our electric field will be either here or here or here or here, etc. But effectively our propagation will move through our direction. So we have an electric field moving in one direction. That's straightforward. We're used to that. I'm going to leave that for 2 seconds, and we're going to go a bit sideways and look at another thing and then bring them back together later on. Okay, so how do we calculate the magnetic field in a current carrying wire? So we've got this lovely electric field that we've been working on, but what does that electric field do to the magnetic field? Well, we have a look at just a straight piece of wire. This is from GCSE. Our magnetic field wraps around our current carrying field. Okay, so it's going to be going in and out of the board. So I always draw this very badly. That's meant to be out of the board, into the board. So it's 90 degrees. Okay, so if I draw it better, it would look, I don't know, 3D. Magnetic field. Someone will tell me off for this one day, but I just simply cannot draw. Magnetic. Okay, so what would that look like? Alright, so in an alternating current wire, this is the point of this slide, you'd obviously have our plus and minus. Not entirely sure why this is, that should be minus, and that should be plus. There we go. So that was hence my hesitation. Why have they suddenly changed? So an alternating current, so as the current goes up and down, our magnetic field is switching around. So when it's up here, our magnetic field is going that way, and when it's down here, our magnetic field is coming out of the board. So our magnetic field is also oscillating at 90 degrees, or in the same frequency as our electric field. Now, the important thing obviously is to remind you, when we have 0, when there's no electric current flowing through here, if I turn this off, none of this exists. So our magnetic field at this exact same point would be 0 as well. Okay, so this slide here, so orthogonal propagation. Oh, this is the one where I show off how badly I can draw. So in terms of, so this is B now. So where we would normally draw B, and it's going to look a little three-dimensional. So it's going out of the board, into the board, out of the board, into the board, out of the board, into the board. You get the idea. And this is orthogonal propagation. Very useful in use for cryptography or in terms of modulating RF signals, so Wi-Fi. Orthogonal propagation is part of how you control your data streams, but that's a very simplified version of explaining it. Okay, so putting it all together, we've learned about electric fields, we've learned about magnetic fields. Well, how do they come together? In fact, they come together beautifully, because one doesn't exist without the other. And hence why we call it, and I've lost my pen for my moment of sensationalism, the electromagnetic spectrum. And this is what the electromagnetic spectrum comes from. With an electric field, we get a magnetic field. And you'll notice that our magnetic field is 90 degrees to our electric field. Okay, and this is probably the most important part of this diagram. It's probably one of the most important parts of this explanation, that when you are at your peak electric field, you will be also at your peak magnetic field, which is intuitive. That makes sense. You've got the most amount of ability to do work, and you expect the magnetic field to be its strongest. And these lovely points right here, where nothing happens, there is no magnetic field because there is no electric field, or vice versa, these are called our nodes. Now the easy way of remembering that is at nodes nothing happens, no movement occurs. Now the opposite to a node is an antinode. I tend to gloss over this a little bit at GCSE, but you may have come across those before. So nodes and antinodes, you just know them as peaks and troughs, but we're talking about max amplitude and nodes here. And there's a node occurring at every 180 degrees, or every pi. Okay, so the SI unit for amplitude, because we talk about intensity and we throw in the word amplitude and people get themselves in a bit of a pickle. So when we're talking about amplitude, we're talking about the largest magnetic force you can generate on electric field strength, for a given electric field strength. So those 2 points, those 2 antinodes I was just drawing in the last slide for you. And the unit for it would be newtons per coulomb. Okay, so our electric field strength is measured in coulombs. And our magnetic force is a non-contact force, but it is still measured in newtons. We can also work this the other way around, and this is where questions get people in a bit of a tiz sometimes. So you can look at the electromotive force or voltage. So I'll just draw that in. Motive force or voltage, and part of an electric field at distance m. Now the distance m we've already dealt with electric fields. We were looking at them before. So as the wave passes, again, we're talking about propagation. We're talking about that lovely sine wave. There's ups and downs, max amplitude and zero amplitude. And that would be just in volts per meter, or Vm to the -1. Okay. Which tells us all the energy in the electric field is equal to the energy in the magnetic field proportionate to c, which c being the speed of light. Which gives us this lovely little equation. So add this to your equation sheet, and the electric field equals the speed of light times the magnetic field, which would tell you, out of these two, which one is the stronger one? The electric field, okay, because this side equals the magnetic field times the speed of light, okay. So the electric field is much stronger than the magnetic field, but they remain proportionate. Okay, so energy is also proportional to the amplitude. Okay, so if we increase the amplitude, we increase the amount of energy, and it's the amplitude squared. Okay, now that's quite useful later on, but for the moment, it's just a summary of what we're seeing in front of us in this diagram. Okay, so intensity often has the letter, I've lost my pen again. The letter S in equations, and it's still represented just like we talked about at the start of the lesson, surface area of a sphere, watts per square meter at a given point on that sphere. And it's the power over the area. Now, power is the energy in a given amount of time. So in this case, we've just times it by -1. Okay, fine, I've done it that way, and just rearranged it into total energy equals the period of time, or the time involved, times the area. Okay, so in this slide, I'd like you to try and derive an equation for me that links amplitude and intensity if time and the area are constant. Now that's quite important. We want to get rid of, I should have done it differently. We want to get rid of time and the area. We want to know how amplitude and intensity come together. So we've seen this one already. So this is our intensity, just to remind you. Okay, that's my equation. So there's my energy, there's my time period, there's my area. Okay, please don't mix that up with amplitude. And over here, this is where this can get confusing. Now it is amplitude, energy equals the amplitude squared. And so when we rearrange, sorry if I'm rushing through this and you can't pause it, intensity equals the amplitude squared over the seconds times the area, which would simplify down to S equals amplitude squared over T. Okay, so on the last slide, I felt like I just rushed through the last bit, but we hadn't yet taken into account removing the area and the time. So to do that, we just want to look at a point where if time was 1 and area was 1, they would be able to simplify out. So you should end up with this equation. I can't rock back and forth through the slides like I normally would, but intensity equals the amplitude squared. And this is just tacked on to the end of this slide. It's going to come into a little bit of use later on in some of the further lessons, in particular when we look at refraction or refractive indexes, and it's to do with this fact that velocity changes. So in space and air, we usually treat those as they equal, but when you change into a different material with a different refractive index or index of refraction, you can see there that straight away slows it down, divided by a number greater than 1, so our velocity will start to, oh, I lost my arrow, start to reduce. Water being a classic example. Guys, that's the end of that lesson. I know it rattles on a little bit, but it should hopefully start to tie up some of those questions about intensity and amplitude you're starting to see on Isaac physics. So again, I won't push you to have that completed just yet, but if you're diligent, I would be going back into there right now, finding any of those questions on intensity and amplitude and making sure you can do them. If you get stuck on any, as per usual, send me an email. I'll hopefully send out a follow-up email tomorrow. I'm just trying to confirm what day I'm in school, and I might do a video chat with you guys and pick a time. If anyone has any particular times they can't do on Wednesday, could you just email me through, please, just so I can not use that time. Otherwise, good luck.